Okay, well, thank you. Maybe I won't answer all those questions right now. So we're going to do this as a split presentation. I'm going to talk a little bit about some aspects of the NeuroVista study and how we collected the patient information that probably aren't so well known, and that's going to lead into a discussion around the statistics of seizures that Philippa will present. Now, a lot of people have been involved in collecting all of this, but and analysing it, but I see Ray Boston just walked in, so I just want to thank Ray especially, and as well Dean and the rest of the NeuroVista team who collected the original data. Now, I won't go through all of the details relating to how the system worked and what its purpose was, only very briefly to give you some background to the slides that follow. But you'll be familiar the NeuroVista device was intended to provide patients some warning of impending seizures, and it did this. It didn't do it for all patients, but it did it for most patients to some degree, and to some patients to a very high degree, a couple of patients of 100% of the time, and gave warning times on average of about 90 minutes prior to an event, but with a range of about 8 minutes to 90 minutes. So it's very long warning times, and warning times that fit with the sort of changes that have been described in a variety of other modalities, such as fMRI and so on. So the patient got a red light if a seizure was thought to be of high risk in the hours ahead, and a blue light if the seizure risk was judged to be very low. Not all patients could have their blue light programmed, but the majority were able to have blue light programmed, and of course if you knew a seizure wasn't coming, that was very useful too. So the aims of the study were primarily to evaluate the safety of the system, and secondly to look at long-term safety conditions and of course advisory performance. Now, the population was the sort of population that would include in refractory trials for new drugs. So there were patients who were all aged over 18 who'd tried at least 2 anticonvulsants and failed them. They had disabling partial seizures and or secondarily generalised events, and they had to have more than 2 a month. And that's probably big enough to read. So you can see the age of the subjects. They're again sort of the ages that we deal with usually in the trials, and a good mix of sexes with this fairly typical range of onsets. But the epileptogenic zones varied quite a lot, so the patients had often been very extensively evaluated and sometimes had surgery for their seizures in the past. A couple had vagal nerve stimulators implanted in the past and so on. But you can see that there's occipito-parietal, parieto-temporal foci, there's some temporal, so there are a couple of patients who had very typical hippocampal sclerosis in the study, and so on. So there's a broad range of locations, and we were able to distribute the electrodes in a variety of ways. So this was one of the suggested dispersions of electrodes over the cortex. This was a frontotemporal pattern. And here's a temporo-parietal pattern, and you can see some co-registered electrodes from a patient who'd had them delivered in such a manner. As I say, all of the patients had been very extensively assessed prior to the study, so they'd all had, generally as part of surgical workup, a very thorough assessment, including always with MRI, scalp recorded ictal events and so on. Most of them had had PET scans. Here we can see the sort of PET scan abnormality that we use to target our electrode distribution in this individual and another patient here. Again, so a lot of these patients had abnormalities out or in or near to eloquent cortex, hence they'd not had resective surgery in the past. There was a mini craniotomy done, so the patients had a mini craniotomy through which the electrodes were delivered subdurally, though some patients who'd had surgery before just had their old craniotomies reopened, so some of them had quite large defects. Here you can see the distribution. I've just got a few of these to run through to show you the variety of distributions. You can see the mini craniotomy here and how the electrodes had been dispersed. We've got very nice recordings from the electrodes. All the electrodes functioned very well throughout the duration of the study. But here you can see some different patterns of distribution. Again, a larger craniotomy in someone who'd had previous surgery. Here's some more complex, trying to get some basal temporal electrodes as well as frontal distribution with the set. And again here. And again here, wrapping through partly into a surgical defect. So there was quite an array of schemes that were utilised, so it was very non-standard in that sense. So how are the seizures classified? Well, the seizures were classified according to whether we could correlate them with clinical events or not. So that the patient's events were typically quite stereotyped electroencephalographically, and we were able to determine that patients were having a seizure either by the fact that they had one witnessed or were able to report it themselves, or that we used audio recordings. Now, the audio unit was in the handheld component of the NeuroVista device and was actually triggered by detected events. So all detected events had audio recordings made. The patient could make an audio recording themselves, and that was the primary purpose of the audio, to annotate the record. But the audio was automatically activated with detected events, and we could listen to that. And it was amazingly possible to detect events even when they weren't reported by the patients or those around them, in a very high proportion of individuals. And that's just a log of the sort of sounds that we were hearing that enabled us to be very certain that a seizure was occurring, the grunting and so on. You could hear people around them describing the seizure or asking if they needed assistance. You could hear them fall over and drop glasses. So you could hear a lot of interesting things. And all of the records had gone through with an automatic system. The events were all then manually gone through again, and then the audio was interrogated. Now, this classification scheme will be very important for the next part of this talk. So typical electroencephalographic events which were accompanied by some sort of clinically correlated activity, whether that be by the patient, a witness, or the audio, are defined as type 1 events. There's a slightly different naming system that we used in the study, but these are the same categories. There were typical electroencephalographic events which were not accompanied by identifiable seizure activity through whichever means. And then there were other electrical events which were dissimilar to the typical events and without clinical accompaniment that we could identify, subclinical events. There were also events that had neither clinical or electrical activity. I'll show you some of them in a minute. And what we found during the study, as has been reported on just now by Andreas, was that there was an enormous disparity between what the patients were reporting and what was actually happening. So at enrolment, patients reporting 7 seizures a month, reporting none during the study, but actually having over 120 events. On the other hand, patients reporting 3 at onset of study, none during the study, and having none. So it was surprising what actually happened during it. Here's a slightly more complicated display of that. So here's the baseline reported events by the patient, actual average monthly events captured, those that had clinically identifying features accompanying them, and those that didn't. So you can see there's huge numbers of these non-clinical events. But here as well, there's quite a lot of events that were reported as seizures by the patient, but not accompanied by electrical changes or by audio abnormalities. Here's another one showing a similar sort of picture, but with lots of clinical events, many more than reported at the onset of the trial. You can see there's very large numbers of clinical events, lots of non-clinical events, and again, a fair number of non-events. Now, just by the way, it was possible, and this perhaps goes to the question that was asked before by Graham, I think, that could you see the effects of treatment? And this is from the dog study, I think, that the Mayo team performed. And here you can see effects of the administration of phenobarb on this seizure risk index as measured here. And we could see similar things in the NeuroVista trial. Generally, the patient's medications were stable during the trial. One patient stopped his medications altogether at the outset of the trial. And other patients took additional medications during the trial as acute therapies, and some took therapies which they themselves had decided might be helpful, often non-medical therapies, to see whether we could detect any change. This is someone, though, who had lacosamide started during the study, and you can see here, so these are clinical events prior to the onset of lacosamide, and here afterwards, so that was very effective. But we could also see that it had a very dramatic effect on the subclinical events. Now, we were very interested in whether we could establish any patterns in the seizure activity, and we've been interested in whether it's possible to demonstrate that seizure activity, in terms of the inter-event intervals follows a power law distribution, and these are images demonstrating for the individual patients the frequency of seizures and the intervals between those seizures. And you can see that when plotted out in the small blue graphs here on a log-log plot, they do, in the patients where there's enough data points, satisfy that there is actually a power law relationship. So other work that we'd done with Andrea Varsavsky, who worked in engineering, was to establish whether it was possible to determine any features of long-range memory in these processes. And if a power law is demonstrated, in some circumstances it's possible to determine if there is evidence of long-range memory in the relationship. As an example here, we were calculating the Hurst exponent as a measure of this. So the Hurst exponent is a measure of whether there is long-range dependence between events, and this is white noise. You can see we're trying to establish the Hurst exponent from this, and there's no significant Hurst exponent here. It's 0.5, and 0.5 means there's no relationship. If it's between 0.5 and 1, then there's evidence of long-range memory, a positive correlation. Here you can see this is actually data from river levels, and you can see river levels demonstrate these long-range memory processes. You can see there's a strongly positive relationship there with a Hurst exponent of 0.91, so there's good evidence of a long memory process in place there. And here, if we look at this in the patients with epilepsy, we could find exactly this relationship. Not in all of them, because we didn't have satisfactory data sets for all of them, not that would allow us to make these calculations. Here, for all of the patients, you can see all the patients where we had sufficient data, you can see that in many of them we could demonstrate these features of long-term memory processes. Just to go through those ones here, so these were the 8 patients in where we had sufficient data to make these estimations, and you can see that we found non-sufficiently stationary data, and enough of them to demonstrate that there was long-range memory in several. But most interestingly, the length of dependence, so these long-range memory processes were over an enormous range of time, so from 1 hour to 1.5 days, 17 hours to 6 days, right up to 20 days here, 40 days here. This is very interesting, and another feature we'll come back to. So there are features of the frequency of seizures that let you pick these long-range patterns. This might also be useful, obviously, with regards to prediction. But there are many other features that will assist us with that also, and I'll hand over to Philippa.
Thanks, Mark. So I'm going to go over some of the preliminary results that we have from this data set so far, and these are quite high-level statistics of the patient seizures that we've looked at. So I'm going to start talking about the distribution of seizure durations and the inter-seizure intervals, and then look at some other temporal patterns in when the seizures are occurring with respect to time of day. So what we see is that there's circadian oscillation in when the patients are having their seizures, but there's also rhythms that are occurring over much slower timescales as well, which is interesting. All of the results that I'm going to be bringing up on the slides today are covered in these 3 papers here. So just starting with looking at the patient's seizure durations and the interval of time that preceded the seizure. So we analysed these statistics using cluster analysis and also mixture models, and what we found was that these distributions tended to fall into these distinct groups, or they were clustered around some characteristic time for the duration and interval, and these times were different for different patients. And also, what was really interesting was that in some patients there were really 2 clear groups of seizure duration and interval, and in others there was just 1 cluster. So I've got an example of that up here. What you can see is a scatter plot of all the patient's seizures. So we've got the seizure interval on the vertical axis and the duration on the horizontal axis, both on a log scale. And you can see from the patient on the left is an example of someone who has two distinct peaks in the distribution of seizure duration and intervals. And you compare that to the patient on the right who has a more dispersed or unimodal distribution. So it's just more one cluster. And these seizures are colour-coded by the types. So these are the types that Mark defined earlier. And you can see there's possibly some relationship where the subclinical seizures are towards the shorter end of duration, but there's also quite a lot of overlap. I have two more example patients here. Again, you can see the bimodal distributions are quite clear in both of these patients. So there's two peaks in the duration and interval distributions. And the patient on the right here has all of their subclinical events falling into the shorter population of durations. So that is potentially what you might expect from subclinical events. But if we can compare that to the patient on the left, there's much more overlap in the events. And in fact, the longest events for that patient were subclinical. So that's the blue colour code there. I'm just looking now at all of these distributions for all 15 patients. So there's quite a lot of information on this slide, but what you can hopefully see is that there are patients, it's roughly half of the patients where they have these two groupings in their seizure populations and others that have more one cluster. And what we don't see a sign of from this slide is a linear correlation between the seizure interval and the seizure duration. So this suggests that seizures are not a process where you have a build-up and a dissipation of energy, because in that case, you might expect to see longer intervals followed by longer seizures, and vice versa, which we're not seeing. And you might also expect to see seizure durations that are falling more uniformly between some physiological bounds, rather than seeing them clustered around this peak characteristic duration. So it's reasonable to sort of hypothesise that if seizures are following some characteristic duration, is there also similarities in the time course of the seizure itself? And we know there are other results showing that if you look at different seizures from the same patient, you can see some similarities or some maybe spatiotemporal signatures in the seizures that the patient's having, which is of course interesting from the perspective of prediction, because if there's some repeating pattern in the seizures themselves, it's possibly more likely that there's a repeating pattern in the pre-seizure state. Okay. So here's a result from our lab a few years ago. This is from Nelson et al. And these results are from induced seizures in a rat model. And what this plot shows is that they were very reliably able to stimulate or induce seizures of two different and distinct durations depending on the precise pattern of the stimulus that was used. So this links back to our patients who also had two clear populations of seizure duration. And what it suggests is that possibly in these patients, there are two durations and two trajectories that their seizures are following. And the relevance of this to prediction is that we found in these patients that had two populations of duration, their seizure prediction algorithm had a worse performance. So just bringing back this demographic table of all the patients in the trial, you can see I've highlighted the patients who only had one duration population in yellow and ranked them according to the sensitivity of the prediction algorithm that was used in the original trial. So there's probably not enough patients to do a real comparison, but we can see there doesn't appear to be a relationship based on gender or age or temporal and non-temporal onset, but these patients are all in the highest sensitivity bracket for prediction. And we think we can use this information going forward because it's quite easy to store on a device to store the duration of patient seizures and potentially classify seizures into two groupings and then train multiple algorithms on these two separate seizure populations. So just moving on now to talk about some other patterns that we've noticed in patient seizures, and anecdotally and historically, patterns of seizures with respect to time of day is not that new, but we've been able to look at it in potentially a lot more detail here. So there's just an example patient shown here. This is a raster plot showing all of the patient's seizures over 500 days in the clinical trial on the vertical axis, and then the time of day that the seizure happened on the horizontal axis. So we can see that this patient has a roughly 12-hour cycle where their seizures are peaking just before midday and then again just before midnight. If we now look at all the patients in the trial, this same histogram, we can see that there definitely are patients who have a clear peak where seizures are much more likely at a particular time of day, and that's quite patient-specific as well. So we can see there are patients who have a peak during the day, so around midday there, and again, other patients who have a peak in the night around midnight or 0. And we can also see patients who have more than one cycle throughout the day, so that two-peaked shape, such as these ones. So again, this is potentially useful and interesting information when it comes to seizure prediction, because these histograms that I'm showing you, once they're normalised, basically represent a patient's prior probability of having a seizure at any given time of day. And that probability is something that we can incorporate into prediction algorithms, which are also hopefully outputting a probability of having a seizure. The other thing that we would really like to know about these patterns is what the underlying mechanisms are. And it's been, hypothesised that, or it's fairly well linked to sleep stages and hormone regulation, but identifying the exact cause of these patterns could also guide treatment strategies. So just to give a bit of historical context to how long people have been looking at this problem, there's a few papers that we've dug up from over a century ago, and this work was done based on an epilepsy colony. That's the photograph there, so colony for children with epilepsy. And you can see that they're also looking at patterns where patients are far more likely to have seizures during the day, during the night, or non-specifically. And the other thing that came out of this early work in temporal patterns of seizure occurrence was that there were rhythms that were happening over much slower timescales. Sorry, I've gotten ahead of myself. So here's the histogram of seizure patterns at time of day. So similar to the histograms that I was just showing you, they're looking at, they've aggregated the seizures over all 66 of their patients, and they're looking at when the peaks are occurring with respect to patients' sleeping patterns. And now onto those longer rhythms. They found examples of periodicity in seizures happening over much longer scales, so weeks to months. And it's been reasonably well documented that in women, sort of monthly periodicity is linked to the menstrual cycle, but they found clear signs of this also occurring in males, and there's no great explanation for that. So here's an example of what I mean by this. This is a plot from one of these papers, and it shows the patient seizures plotted against the time of month. So you can see in those last 3 patients, who are all male, they've got this repeating pattern about once a month. And as Mark mentioned, we looked for signs of these longer rhythms in our patients too, and in those with enough data, we did tend to see evidence that seizure dynamics are governed by this long-range dependence or have a long memory. So Mark showed you the Hurst exponent results, and we also looked at this using the autocorrelation in the number of seizures. So here's just a couple of example patients of that, where you can see if you look at the autocorrelation in seizure number over lag times of out to 30 days, we see significant correlations on the left-hand patient happening around a week or a fortnight, and on the right-hand side all the way out to 1 month. And so autocorrelation is a sign of repeating patterns in the data. So what this suggests is that there are quite slow underlying processes regulating seizure likelihood. And in addition to changes that happen on very fast timescales, prediction also needs to take into account these really slow regulatory mechanisms. And knowing a bit more about these regulatory mechanisms and how they impact on seizure likelihood would again be helpful in guiding treatment strategies, potentially. So 50 years ago, they thought the obvious place to look for answers to this problem was that people with epilepsy were in fact werewolves. And so they looked at the lunar cycles to try and find some correlation there. So there's a quote that I quite like from one of these papers. "The time structure of epileptic rhythms has not as yet been studied by means of computer techniques, which leaves a good many male epileptics with 28-day periodicity still staring at the moon for an answer." And we're still actually looking to the moon for an answer. So I've just done a quick Google Scholar search with keywords of seizure and moon, and quite a few papers come up. So Moonstruck is my favourite. I think the consensus on reading a lot of these papers is that if anything, the moon cycles are negatively impacting the quality of people's sleep just due to illumination changes, and it's probably that if there is a positive correlation found, it's probably due to sleep quality. So this last paper here, just from a couple of years ago, found that the lunar cycle could negatively impact on patients' sleep quality, so potentially that's the answer there. We won't rule out werewolves though. So we've looked in our data as well for signs of this occurring. So what you can see here is the total seizures per patient, and just taken an average over all the patients and plotted with respect to the phase of the moon. So it's a nice looking plot, but if we actually do the analysis, it's quite definitive that there's no effect from the phase of the moon. So now we know. And anyway, these statistics aside, I think we can learn a lot from these quite high-level results of seizures, and the key things to take away are that in prediction we should account for the potential of multiple seizure populations, and that was indicated by the different clusters of duration and interval, and that had an impact on the predictability for those patients. We can also be looking at the prior probability of seizure that's occurring with respect to time of day, and not just circadian rhythms, but also much longer term processes that are having an impact on likelihood of seizure. And so all this work is the result of a big team here, so thanks to them and thanks for your time today.
Mark, that's the first question. Was that true over the moon in all patients?
So Mark wants me to show you a particular slide, I think. So yeah, the reason we couldn't find an influence of the moon is because there's quite a lot of variance in the number of seizures patients are having, but you would hypothesise that a werewolf is quite a rare occurrence. So if we look at the patients individually, we can see that there might, so these plots show all of the patients plotted with respect to the moon. And we found one who, has obvious signs of werewolf tendencies.
I wondered if you looked at this apparent phenomenon that struck me on a number of occasions quite frequently of when you introduce a new anti-epileptic drug, there's often a prolonged period. The person doesn't have seizures and then they start having seizures at the same previous frequency. Is there any sort of evidence that is based on your observations about seizure interval or etc.?
We haven't done any analysis with our seizure data with respect to the drugs that the patients were taking, but we definitely have that information, so it's something we probably can and should look at. And Mark might be able to add to that because he was involved more during the trial.
We didn't really, other than that example I showed you with the lacosamide, the only other variation made to the therapy during the trial was in the latter phases patients were given clonazepam or some patients were given clonazepam when their light went red on the prediction device to see if a seizure could be prevented. And although we didn't acquire enough events to make any confident statements about it, it certainly did seem to have some influence.
Any other questions? Yes. Because we can pick many different statistical distributions to experimental data. I wonder whether there were any goodness of fit tests performed to validate that these distributions are really favorable.
Yep, so the distributions of seizure duration and seizure interval.
Interseizure intervals, yes.
Yep. So we did quite a number of different methods of analysis on the results, and the method of validation was that all these different methods were lining up and providing the exact same mean and variance and proportion when we're looking at clusters of or distributions of seizures. So we looked at different mixture models and also k-means cluster analysis and a number of other methods, and they all lined up and gave really similar distributions. Sort of hard to give a goodness of fit when we don't have a ground truth, I think, but yeah.
That was really very, very interesting. So it looked like the ones that there were patients that had two characteristic timescale events. And maybe you don't have enough, even though you got lots of data, maybe you don't have enough. Is it possible that some have multiple characteristic timescales within those? Or do you think it is pretty much this pattern of, if they have this phenomenon, they might have a long time scale for characteristic events and then a short time scale, which clearly a lot of patients have that, of course. They have their event and then they have their subsequent cluster of seizures, which, and I have a slide I'll show later that I think you'll appreciate. Very similar phenomena in some dogs as well. Very long time scale and then some short time scale events. In some cases, then multiple kind of seizures. Yeah.
You've really hit on where we're taking this work currently, so things that we're working on the moment, which are exactly as you mentioned, looking at much longer timescales, and then within those when seizures might be occurring in little clusters, and then going again down the spatial scale to smaller events, and how they also fit into this time process.
So the Neurovista forecasting, I mean, they didn't have anything like that, right, Mark? Where you would have a hazard model that would, you would increase your probability that would be peaked around whatever the characteristic time scale that patient had.
That's right, it didn't, and that would be useful to include. Obviously, I guess in the first part of your question there, another aspect is whether, I think what you're asking as well is whether the patients with single populations had, a set memory cycle for them, but they didn't. Certainly from the Hurst exponents and in the autocorrelations you can see it as well, whether they had one or multiple populations, they'd still demonstrate this feature. So, because it was an initial thought that maybe we're just catching those two populations running on different cycles, but that doesn't seem to be the case.
Didn't you find a relation, when we dichotomized both the duration and the interval, you said that there was not a correlation, but there was a probabilistic relationship, wasn't there, I think, between the particular group, the long and the short duration and the long and the short interval. Is there
Sure.
what we're talking about? Or?
So there wasn't a linear correlation in that you didn't see points on those scatter plots falling along the diagonal as you would for a linear correlation, but there was a logistic correlation. So if we look at the log odds with the short population and the long population, and if anyone's interested in hearing more about that, I'll point them to Ray after the talk.
Well, actually, Ray might like to comment on the relationship of the interval and the magnitude of the clinical event.
Well, you want me to talk about the very recent work or what we...
Well, I was thinking about that, what you did where we examined the possibility that a more significant clinical event followed a longer interval.
Well, it's not sure the question was, let me just say that there is definitely relationships between what we did. We split the durations into two populations you saw there, and we split the interval into two populations, and they did. You know, it wasn't juggling the numbers. You could see clearly populations, and we used statistical methods as well, cluster analysis to split the population. So we had the partitioning between these two features of seizures, and we did find a very striking relationship between what the interval implied in regard to where the subsequent seizure would be linked. You know, in this analysis, I realised that we sort of looked at the whole business the wrong way, because really it's the interval that drives. The interval that drives the duration rather than the duration dividing the interval. Remember that, Philippa, and we had to sort of get the corrections onto the right line. This is a vast data set, by the way, but we had to get the duration onto the right line. And I'm sure that we, in fact, found strong relationships that long intervals led to long durations. And so it wasn't a linear correlation, it was a probabilistic correlation, which means somehow you have to, tease out odds in terms of the likelihood of an outcome falling into the short or long duration. I think it's not something to throw away. I think there's something we can build on. It's particularly, we only had probably about 6 or 7 subjects with these populations, but that's, the two durations and 2 intervals. But that was 6 or 7 out of 14 or so, so it wasn't a bad representation. It's just that it's small in regard to a study that might be able to strengthen that relationship.
I might add, the other important point is there wasn't only 2 populations. There was 3 populations of durations for some of the individuals.
That's correct, yeah.
And possibly even more than that, but that's the limit of our resolution with the statistics. But it did, if you look at the graphs, there certainly appears in some of the individuals to be 4 populations. That's one point. But the duration populations always seem to fall into 2 categories, didn't they?
That was very nice. Just was wondering, and maybe your data set and also the dog data set, which is up on IEG, would provide an opportunity for what did you look at the effects of therapy changes on these time constants or on these intervals? I think clinically we all appreciate that changes in therapy, changes in drugs and doses will often affect these in terms of the clinical clustering of seizures. I'm wondering if you looked at that variable across these.
No, we didn't, Brian, just because we didn't have much in the way of drug changes across the trial. The one example I could pull out was the lacosamide, and the others were only the benzodiazepine used acutely towards the end. So there was nothing in there that we could really pull out. But it'd be fantastic information to have, and that's certainly something we're looking at with our dogs.
Right.
well, it's now time for morning tea, which is out in the foyer out there. We'll reconvene.